The needle EMG and nerve conduction recordings are performed in the extracellular space called the volume conductor. The volume conductor is essentially the highly conductive body tissue which facilitates the electrical fields to spread away from the generator site. An example of such recording is the electrocardiogram, where the electrical activity of the heart can be recorded remotely at the limbs. The shape of the potential recorded in the volume conductor reflects the electrical events at the generator site. For proper interpretation of the signals in EMG and nerve conduction studies, it is important to understand the relationship between the extracellularly recorded action potential to the propagating intracellular action potential. The nerve or muscle fiber maintains a resting membrane potential of roughly minus 80 millivolts, the inside of the cell being negative. When stimulated, sodium channels open. This causes a flow of positively charged sodium ions into the fiber and makes the intracellular space positive. This is the depolarization phase. We will consider the inward flow of positive charges as a positive current. Very shortly, the sodium channels are closed and the potassium channels open. The positively charged potassium ions move from the intracellular to extracellular medium. This is the repolarization phase. Note the opposite direction of flow of charges. Hence, we will call this a negative current. The flow of potassium ions causes a slight hyperpolarization of the fiber. Hence, additional positive current is needed to bring the fiber back to its resting state. This is indicated by a small positive current. The three current sources represent the so-called tripole model to study the extracellular action potential. One can increase the number of current sources to improve the accuracy of numerical calculations. As example, one can split the central negative current into two current sources. This gives us the so-called double dipole model. A pair of equal but opposite current sources is called a current dipole. The first dipole is called the leading dipole, while the second dipole is called the trailing dipole. I will use the double dipole model to explain the shape of the extracellular action potential. In this schematic, we have a muscle fiber in a volume conductor. We are recording in the extracellular space as the muscle fiber action potential travels from right to left. Initially, the muscle fiber is at rest and we see the signal baseline. When the action potential propagates towards the electrode, the positive current source is closest to the electrode. Hence, it records a positive voltage. On the electromyograph, a positive voltage causes a downward deflection on the display. Hence, we see the signal move below the baseline. When the positive current passes and negative current source approaches the electrode, the signal changes its direction. We see the sharply rising positive to negative phase or the rising phase of the potential. As the leading dipole moves away, the voltage recorded by the electrode decreases. However, it is still negative due to the approaching trailing dipole. When the trailing dipole passes under the electrode, we see the terminal positive phase of the potential. As the tripole moves away to the tendon, the potential returns to the baseline. This simple model explains the triphasic shape of the extracellular potential, although the intracellular action potential is relatively monophasic or biphasic. A similar analysis can also be performed using the so-called solid angle model. Since it gives similar results, I will not discuss that approach. Here are some additional important results from these models of extracellular action potential. The potential generated by a current source is inversely proportional to the distance from the recording site. Hence, the extracellular action potential amplitude also depends on the distance between the nerve or muscle fiber and the electrode. If the distance is increased, the amplitude decreases. This explains the change in signal amplitude when the needle position is changed in motor unit potential recordings. In sensory nerve conduction studies, the amplitude is lower when recording from deeper nerves, or when there is excessive fat tissue, or when there is edema under the recording electrode. Let us consider a muscle fiber action potential recording by two electrodes, P and Q, that are at different distance from the end plate. When the muscle depolarizes at the end plate, both electrodes register this event as a positive voltage. Both recordings show an initial downward deflection. When the leading dipole of the potential arrives under electrode Q, the positive phase ends and the negative phase of the potential begins. At that time, the electrode P still records a positive voltage. When the action potential arrives under electrode P, the positive phase of its action potential ends. Note the positive phase represents the propagation of action potential to reach the recording electrode. This is also called the arrival of action potential at the electrode. The initial positive phase has a longer duration when the electrode is farther away from the end plate. If the electrode is brought closer to the end plate, the action potential arrives at the electrode earlier, and the duration of the positive phase is reduced. In a limiting case, if the electrode is over the end plate itself, there is no arrival phase at all, and the action potential will not have the initial positive phase. The potential is biphasic with an initial negative or upward deflection. We see this routinely when the needle EMG contains the end plate spikes. An initial positive deflection can occur from volume conducted activity from other muscles. In this example, the median nerve was stimulated at supramaximal intensity and gave a response with initial upward deflection. When stimulated at much higher intensity, the response looks quite different. With higher intensity, the ulnar nerve was also stimulated. The volume conducted signals from the ulnar innervated muscles are reflected in two ways. First, there is an initial positive deflection. Secondly, the CMAP amplitude is much higher. The excessive stimulation, a common pitfall, can be recognized by contraction of additional muscles, resulting in movement of additional anatomies. Hence, it is important to look at muscle contraction when motor nerve conduction studies are performed. As a result of volume conduction, the E2 electrode also records the muscle action potentials in a motor nerve conduction study. This is often not appreciated. We recorded the compound muscle action potential with ulnar nerve stimulation at the wrist. The E1 electrode is on the muscle belly, and the E2 is placed distally over the small finger. The CMAP shows a typical waveform with a small plateau just before the negative peak. We then moved the E1 electrode over the contralateral hand. It is so far away that it should not be able to record any significant response. Whatever signal we record is the potential measured by the E2 electrode. And here is the waveform on the bottom trace. There are three interesting observations. First, the signal recorded by E2 electrode is quite large. The baseline to peak amplitude for this signal is 6.6 millivolts, and it is 77% of the standard compound muscle action potential amplitude. It is quite obvious that the E2 electrode makes a large contribution to the Cmac. Next, we notice the onset latency for the two signals is the same. This is expected from our previous discussion that the muscle depolarization at the end plate is recorded at the same time at different electrode positions in the volume conductor. Finally, the peak of the compound muscle action potential is defined by the signal from the E2 electrode. Indeed, the E2 electrode has a great influence on the shape and measurements of the compound muscle action potential. Hence, the E2 electrode position should also be standardized in motor nerve conduction studies.